Alright, hello class. Today we're going to be talking about section 4.1, which is on maxima and minima. Now chapter 4 is all about applications of the derivative. Okay, so now we looked at a lot of applications already. I mean, it's hard to talk about derivatives without talking about, velocity and whatnot and related rates and all that, but here these are maybe moving away from physics examples into other types of applications. And the first thing we're going to be talking about are maxima and minima. And this section in particular is all about local maxes, global maxes, or absolute maxes. And I'm not going to spend a lot of time in this early definition, but a local max is the highest point of the graph. Okay. Locally, and you really shouldn't use the name in the definition, but it's kind of opposed to the absolute max. Sometimes you'll hear me call this a global max, which is the highest point of the graph overall. Okay, so what I mean by that is if, let's say, I have a graph that looks like this, okay, and right, the highest point of the graph overall is right here. So here's the absolute max. But this is also considered a local max, right? Because it's not the highest point overall, but it's the highest point close by, right? So the highest point close by. Okay, and actually an absolute max is also considered a local max. Okay, and in fact the local maxes and mins are so important that I kind of just drop the local and just say they're maxes and mins, and when I want to verify a global or absolute, I'll actually say that word instead. And we can say the same thing about minimums, right? This is a local min, but we don't have a global min because there isn't a lowest point, right? No lowest point, so no absolute min, right? And that's because the graph keeps on going towards the south, so to speak. Okay, so I'll look at a couple other examples quickly. All right, if we check out this graph here, here's the axis. And this point, that's of what I see of the graph, is the highest point of the entire graph, so it's a absolute max, and which also makes it just a max. And here is the absolute min, right? Because there's the lowest point of the graph overall. And so we have both an absolute max and an absolute min. Okay, but for example, a similar kind of graph here, if I have a graph that looks like this, I have, well, a local max and a local min. Okay, but no absolutes. And that's because, well, I keep going up to positive infinity, so if I actually stop and say, hey, this is the highest point, well, I have an infinite number of higher points up here, and the same down here. If I say that this is the lowest point overall, then I can say, well, I have an infinite number of points below. But I still have a local max here and a local min here, local max here, because this is the highest point locally. And it'll be the highest point, say here, in this circle I've just drawn. And for a lot of the graph, it's actually the highest point. And then same here, this is the local min, because it's the lowest point for a while until you get over to this side. Now this is all fairly straightforward and whatnot, for the most part, until you get to something like this. The global max is right here, and there I am again calling this a global max, but the absolute max is here because this is the highest point of the graph total. But we have to be careful because we might be tempted to say that this is an absolute min, but actually it's not, because the graph never reaches this point. Okay, so we have no absolute minimum, right? Because we keep getting closer and closer and closer to 0 here as we come down, but we never actually get there. So we can't actually pin down a point and say that that is the lowest one on the graph at all. So keep in mind that open circles, open points, right, cannot be extrema. So I'll just say, I've done this twice in a row now, extrema, which is a word that just accompanies both. Okay. So for all these examples, our global maxes and mins, okay, our local maxes and mins, and here's where we get to the calculus of it all, except for this example, but we'll come back to that. Let's take a look at the tangent lines of what's happening at these maxes and mins. Right? So if I look at the tangent line here at this absolute max, I have, well, basically a horizontal line. Okay, and at this absolute min, looks like I also have a horizontal line. Okay, and at this local max, I have a horizontal line, and at this local min also a horizontal line. Okay, so at these local maxes and mins, so at local extrema, what I see is horizontal tangent lines. Right? The slopes are 0. So what I have is that the derivative, so the slope, which is given by the derivative, let's say f prime, is 0 at these points. Okay? And if I go back to the first example, at all of these turning points, I have that, well, a horizontal tangent line, horizontal tangent line, horizontal tangent line. Okay, so 0 slope, 0 slope, 0 slope. So these are all places where the derivative is equal to 0. Alright, so now that we have this, this means that if we were out in the wild looking for maxes and mins, which is an important thing to do. I mean, think about if you have a profit function, right? This function models your profits, the money that you're making, after you break even and all that. Where would you want to stop? You'd want to maximize that, right? Or if you're dealing with a cost function, you might want to minimize that. So a place to look is where the derivative is equal to 0. So when given a function, okay, you might think to find extrema, you might think, well, we'll look at where the derivative is equal to 0. Okay, and that's true. Okay, that's very true. If we want to maximize or optimize something, one good place to start is looking at where the derivative is equal to 0. But one thing we need to be really careful about is the fact that we have some situations that might trip us up. Say, for example, if I look at the function f of x equals x cubed, right, it looks like this when you graph it. Okay, and if I take the derivative, I get 3x squared. And actually, this guy's derivative is 0 at 0. Okay, but I don't have a max or a min here. I actually have what we might call a leveling off point, but this is still where the tangent line is horizontal. So note that x cubed has a horizontal tangent line, okay, line, okay, at x equals 0, but not a max or min. Alright, so just because you have the derivative of 0 does not automatically mean you have a max or min. It just means it's possible you have a max or a min there. So it's only possible that you have a max, or I'll just say an extrema, when f prime equals 0. Okay, it's also possible, so you might also have a leveling point, which is what I like to call these points, where the graph kind of, it doesn't stop increasing, but it just kind of, well, it does actually for just a second, but it kind of levels off for a minute and then keeps going. Okay? And we'll talk more about this type of thing in section 4.2. Those who've seen this before probably recognize this as an inflection point. Okay? And another thing we need to be concerned about is, take this graph. Actually, let's see here. Okay. So here we have the global max, or I did it again. The absolute max is here, and the absolute min is here. Okay, but these aren't smooth curves, right? So the derivatives here aren't 0. In fact, here the derivatives don't exist. The function is not differentiable here. Not differentiable at these extrema. Okay, but there's still extrema all the same. There's still an absolute max, or you could even think of it as a local max, as if these kept going. Okay. So what this basically means is that we also need to look at places where the function is not differentiable. And again, it's possible that we might have some places where the derivative doesn't exist that aren't local maxes or mins either. So what has happened because of all this, we need all this information all together in a single term. So what we say is, we have a word for this, and what we say is it's a critical point. So here we go with the definition of a critical point. If we have a point C in the interior of the domain of f of x, so what that just means is that critical points can only be in the domain of f. So if f itself does not exist at a certain point, then you can't have a critical point there. But that will be important a little later. But basically, a point C is a critical point of f, okay, if either f prime of C is 0, so either the derivative is 0 at C, or f prime of C does not exist. Okay, so one of those two things happens. And what we say is that local extrema, okay, basically only happen at critical points. So critical points are where local extrema occur. Okay. So a lot of this section is about finding critical points. So let's look at some simple examples. But basically, to find critical points, right? So to find critical points, we basically find f prime of x, then set equal to 0 and solve. Then also and find where f prime of x does not exist. Alright, so let's look at an example of how you might do this. A really simple one to start with. Okay, so let's find the critical points of this function f of x equals x squared. Something very simple, but something where we already know the answer. Right, x squared looks like this, and we already know that it has a global max here at 0. Okay, so what we're going to do is take the derivative to x and set it equal to 0. Right, so critical points happen when the derivative is equal to 0, and what I usually do is when I'm actually setting something equal to 0, I use a three-pronged equal sign just to kind of show what's going on. And when we solve this, we get x is equal to 0, meaning that x is the critical point of f of x, right? Which we already knew. The critical point of x squared happens here, right? That's where we have the horizontal tangent line, and we don't have to worry about where f prime doesn't exist, since, you know, 2x is a nice function. Okay, to give an example of something where, say, the critical point comes from a place where it doesn't exist, let's consider f of x equals x to the 2/3. Okay, x to the 2/3. If I want to find the critical point, I hope you don't mind from now on that I start calling these CP, just because we're going to use this a lot. But to find the critical point, basically find the derivative, which will be 2/3 x to the negative 1/3. I'm going to set this equal to 0. But here's the thing. If I rewrite this, first of all, I could multiply both sides by 3/2 to sort of get rid of that constant. So I basically have x to the negative 1/3 is equal to 0. I basically have a fraction with an x in the denominator. This will never equal 0. So there's no solution here. Does that mean that there's no critical point? Well, there's no critical point such that the derivative is equal to 0, but, okay, but note that 1 over x to the 1/3, or let me just say 2/3 x to the 1/3 there in the fraction, this thing is undefined at x equals 0, right? Because if we try to plug 0 in, we get division by 0. And since this thing is undefined or does not exist at 0, this means that 0 is a critical point of the original function x to the 2/3. Okay? And if you look at the graph of x to the 2/3, it looks a lot like this. Okay? And so it has a non-differentiable spike here. Right? So not differentiable, but still the global min, I did again, absolute min, global min, it's interchangeable. Okay? So this is why you actually have to check both. So now that we have a way to find critical points and talk about them, I'll do some more examples as we do examples of other things. But basically, we're going to use the extreme value theorem here because 4.1 is concerned more about finding absolute maxes and mins versus finding locals. We'll look at that in 4.2. But basically, we're going to use the extreme value theorem, which basically says that a continuous function f of x on a closed interval, a to b, must attain both an absolute max and min, so both extremes. Okay, and if you think about it, if you have a continuous function on a closed set, a to b, you can't really draw it without having both an absolute max and an absolute min. Okay? You can go ahead and give it a shot if you don't believe me. Try to draw a continuous function from a to b that doesn't have both a max and min absolute. And we're going to use that piece of information with this, in that local maxes are going to occur at critical points and absolute maxes can occur at endpoints. So that means absolute extrema can only occur at endpoints or critical points in this set. And what I mean about endpoints are like the points A to B here. So if we want to find, to find absolute extremes, okay, basically, one, you find the critical points. Okay. Then two, you evaluate f of x at the critical points and endpoints and see which is highest and which is lowest. And that's really all you have to do. Okay? Find the critical points, okay? Then you plug in the values into the original function of the critical points and the endpoints and just see which is highest, which is lowest. Okay, so let's take a look at some examples to show what I mean. And this will involve both finding critical points and evaluating them with the endpoints. Okay? All right, so let's find the absolute extrema of this function here, f of x equals x to the 4th minus 2x cubed on the interval -2 to 2. Okay, so first we need to find the critical points. And to do that, what we're going to do is take the derivative, which is f prime of x, which will be 4x cubed minus 6x squared. And then we're going to set it equal to 0 and solve. We could also try to find where it does not exist, but this is a nice polynomial. It's going to exist everywhere. It's continuous, all that, so we don't have to worry about that second piece. So we're just going to set this equal to 0 to solve, and I always recommend that you factor first. We can take out an x squared. We can also take out a 2, so we get 2x squared. And when we factor that out, then we'll be left with a 2x minus 3. Okay. So we get 2x squared is equal to 0, or 2x minus 3 is equal to 0. So actually, let me go ahead and write this out. For those of you who are unfamiliar with your algebra, well, you'll need to get there quick. But I have 2x squared is equal to 0. This tells me that x is equal to 0, and 2x minus 3 equal to 0. This tells me basically that x is equal to 3/2. Okay, so these are my critical points. 0 and 3/2. So that means I know, well, we have horizontal tangent lines at 0 and 3/2, meaning I've got to have something there, right? Okay, so something's going on there, either local maxes, mins, what have you, but we're only looking for absolutes, and so to find absolute extremes, okay, we basically plug in the endpoints and the critical points back into the original function f. So I just go in order, right? F of -2 is going to be, I like to use the factored form of f when I do this, but it doesn't really matter. But it will be -2 to the 4th minus 2 times -2 cubed. Okay, and that is going to end up being 32 when it's all said and done. Okay. Then I'm going to do f of 0. Okay. So f of 0 is simply 0. Then I'm going to do f of 3/2. Now this one, it's nice to have, well, it's nice to have our calculator for that. 3/2, so it'll be 3/2 to the 4th minus 2 times 3/2 cubed. Can't really see f. Okay. So let me go ahead and plug that in and see what we get. Alright, so you get something messy. I got -27/16, or this is equal to -1.6875. And then finally, when you plug in f of +2, you'll get 2 to the 4th minus 2 times 2 cubed, which is going to be 0. Okay, so which is the highest value? Obviously 32. Okay, and which is the lowest? Well, that's going to be -1.6875. So this 32 is the absolute max, and this -1.6-ish is the absolute min. Okay, and that's basically what I mean by you just plug the values into the original function and see which is the highest. Now you've got to plug it back into f, not f prime. We're done with f prime once we find the critical points. After that, then we're just plugging in to find the absolute max and min. So the absolute max is at -2, the absolute min is at 3/2. And when we graph this function, okay, it looks a little like this. Okay. So let's see here. Okay, so here at 0, it's got a little leveling off point, and then at 3/2 it has its, which will actually be here, has its turning point. And this is totally not drawn to scale at all, but this is kind of the idea of what it looks like. We actually have a leveling off point, crap, sorry about that, here at 0, and a local, and a global min here at 3/2, and we've got 0 at this endpoint and the global max here at -2. Okay. Now, we will look later at how you can graph these with this information. That's section 4.3, I believe it is. But don't worry about that just yet, but eventually we'll get there. Okay, I just wanted to show you all what it looked like. Okay, let's look at another example. Okay, let's look at another example. We're going to do the same thing here. We're going to try and find the absolute maxes and mins, absolute max and absolute min of this function here, f of x equals x to the 2/3 all times 2 minus x. Now, there are a couple ways we could do this. We could use the product rule, okay, or we could also use, we could distribute this across if we wanted, because first we need to find the critical points. Alright, so it doesn't really matter which way you do this. I'm going to go ahead and distribute this across, right, so that f of x is equal to 2x to the 2/3 minus x to the 5/3, right, because this is x to the 1. When you distribute that across, you get x to the 5/3. Right, and now it's just power rule, so this saves me from having to do the product rule. So I'll get 4/3 x to the -1/3 minus 5/3 times x to the 2/3. Okay, now this is kind of a crazy problem to deal with, because it's going to involve both. We're going to have both a place where it equals 0 and a place where it's undefined. So what I would do is the following. I would rewrite this as a fraction so that it's 4 over 3 times x to the 1/3 minus 5 times x to the 2/3 over 3. And now we can actually get a common denominator, because the only thing missing over here is x to the, x to the 1/3. Okay, so I'm going to go ahead and multiply by x to the 1/3 over x to the 1/3, and that gives me, I'm going to simplify it down. Now I have a common denominator, and x to the 2/3 times x to the 1/3. This is going to come together to give me x to the 3/3, which is just x. So on the top, I'm going to have 4 minus 5x all over 3, x to the 1/3. Okay, so that is f prime. Now you might wonder why I did all that work, and it's because now I have two things I'm going to want to do to find critical points. Right? First of all, for critical points, the first one is f prime of x equals 0. So this is going to be 4 minus 5x all over 3x to the 1/3 is equal to 0. Okay? And that, well, the only time a fraction is ever equal to 0 is if the top is equal to 0 and the bottom is not. So this happens if and only if 4 minus 5x is equal to 0. Okay? Or you could just multiply both sides by 3x to the 1/3 and cancel that out. And what this means, or what I get now, okay, is, sorry, I didn't mean to raise it that far, is a critical point of 4/5. Right, so there's one critical point. Okay, the next one is now, so next we're going to look at f prime of x does not exist. And that if f prime of x is 4 minus 5x all over 3x to the 1/3, this doesn't exist when the denominator is equal to 0. So this does not exist when 3x to the 1/3 equals 0, which now gives me another equation to solve, but it's very easy. 3x to the 1/3 is equal to 0 if and only if x is equal to 0. So that is my other critical point. So the critical points are x equals 4/5 and 0. Okay, so there are my critical points. Took a little more work this time, but now is when we really want to start simplifying our derivatives, because we're going to have to start setting them equal to 0 and solving, trying to find when they don't exist, all that kind of stuff. So here's where simplifications are really going to be important. Now, is that the only way you have to simplify? Well, no. But keep in mind, you've got to be careful, because if you aren't, you might miss out on some of the critical points that you actually need. Okay? So, moving on, now remember we are only trying to find the absolute maxes and mins. Right? So to find the absolute extrema, now we just start plugging these values in. So we have the endpoints. If you remember what the endpoints were, the endpoints, going back to the original, are -1 and 2, and then our critical points are 4/5 and 0. So I'm going to write the function down again, the original function, which is x to the 2/3 times 2 minus x, and start plugging things in. So first, remember this is on -1 to 2 with critical points x equals 4/5 and 0, just so I have it all on this same screen. So f of -1, well, this is going to be -1 to the 2/3 times 2 minus a -1. Now, -1 to the 2/3, well, that 2 is going to make that positive. Okay, and so that's just 1. And then we have what's in here, which is 2 plus 1. So the whole thing ends up being 3. Then next up is 0, if I go in order. So 0, I'll get 0 to the 2/3 times, it doesn't really matter what else, because that's just going to be 0. When I plug in 4/5, okay, it's going to be 4/5 to the 2/3 times 2 minus 4/5. And this is one I think my calculator might help me out with. 4/5 to the 2/3 times 2 minus 4/5. And you get something fairly nasty here. It's 1.034, and that's good enough. Okay, remember, we're just trying to find what's the highest and lowest point, so it doesn't have to be exact. And now when I plug in 2, because that's my last endpoint, I'm going to get 2 to the 2/3 times 2 minus 2, and that comes out to be 0. Okay, now if I go through and look, what is my highest point overall? And that's, of course, 3, so this is the absolute max. And what's my lowest point overall? Well, it happens in 2 places. It's going to be here and here, 0. So these are both my absolute min. So you can have multiple absolute minimums. They just will occur. So really the minimum is 0, but it occurs at 2 places, at 0 and at 2. Okay, that can happen often. Take, for example, a trig function. Right, a trig function sine oscillates back and forth from -1 and 1, so its absolute max is 1, and the absolute min is 0, or excuse me, is -1. They just occur an infinite number of times. Okay, so that's definitely possible. And that's what we have in this case. We have the absolute min is 0, but it just happens to occur twice. And if I was to look at the graph of this function, ignore the sine function for a minute, now the graph of this guy looks something like this. 0, it's 0 at 1, or at -1 we found it was 3. Okay, and at 1 it was, something, doesn't really matter. I'm not looking at 1, it's 4/5. Okay. 4/5 will be somewhere like here. Anyway, so this guy looks something like this. Okay, so it has a horizontal tangent line here. It had a place where it wasn't differentiable there, and there you go. Okay, and here's the absolute max, and here's the absolute min, both at 0. Okay. All right, let's look at another example. Okay, let's do the same thing for f of x is equal to sine squared of x on the interval 0 to pi. Okay, so first thing we need to do to find critical points, right? So to do that, we have to take the derivative. And in fact, in chapter 4, if you guess that your first step is always to take the derivative, you're pretty much right every time. And that also means that on this chapter 4 material, if your first step is not taking a derivative, or you do a bunch of work and never take a derivative at all, you've done something completely wrong. Okay, so you'll always be taking derivatives in chapter 4, always. So, to find the derivative, this is going to be a chain rule. Now, you might like it written better like this, sine of x squared, but eventually, hopefully, you'll get used to the fact that sine squared x is sine of x all squared, and when we take the derivative, it will be a chain rule, so this will be 2 sine of x to the 1 times the derivative of sine, which is cosine. So I get 2 sine x cosine x. All right. Now, okay, we want to find the critical points, and to do this, well, we have two choices. The one is when the derivative is equal to 0, and the other is when the derivative is undefined. Now, sine and cosine are continuous everywhere, so the product will be continuous everywhere. So we only need to worry about when it is equal to 0. Okay? So when sine x times cosine of x is equal to 0. Now that's going to happen. That means that either I have two things multiplied together giving me 0, so this is going to mean that either, and I don't have to worry about the constant, either sine of x is equal to 0 or cosine of x is equal to 0. Right? And we're looking at the unit circle from 0 to pi. Okay, so the places that will make sine equal to 0 there are 0 and pi. Okay, and the places that will make cosine equal to 0 between 0 and pi is going to be pi over 2. Okay, so these are our critical points. And note, two of them are actually the endpoints. Right? So when we go to find the absolute maxes and mins, so I'll say Extrema, alright, what are we going to do? Well, we're going to plug these values back into the original. And this is also why it's very important that you label everything so you know what you plug things back into. And think about it very carefully. we're looking for the y values. We're done with the derivative. We're now looking for the y values. Okay, so I'm going to plug in the endpoints. So f of 0 is sine squared of 0, which will be 0. Okay, f of pi over 2 is going to be sine squared of pi over 2. That'll be 1. Okay, and f of pi will be sine squared of pi, which will be 0 again. So this becomes the absolute max, and these two guys are the absolute min. Okay, and the graph of this sine squared from, say, 0 to pi, you know, it's going to look something like this. Okay, so we have endpoint there, and actually it's a little curvier here at the endpoints. Okay, so it looks something like this, and if we were to continue this graph on, you would actually have local mins here at pi and 0. Okay, but they happen to be endpoints here. Okay, and that's all I really wanted to talk about here, give an example of a trig function. Just remember, if you're finding absolute maxes and mins, all you've got to do is find the critical points and then plug it and the endpoints back into the original function. And again, that is why you've got to label things and be very careful. Okay, so that'll be it for this section, and we'll get deeper into these ideas in section 4.2. I'll see you all then. Cheers.